This is a demonstration of Delta Computer Systems second order control and how we can reduce the need for having a high ratio of the natural frequency to frequency of acceleration. Below you can see a 300-pound mass, approximately 300 pounds mass, being moved by a 1-inch diameter cylinder. This is not the way to design a system. The diameter of the cylinder is purposely designed to be too slow or too small so that the natural frequency is about 6 hertz. The only reason why this system is controlling as well as it does is because we're using our second order control. I've stopped the plot. You can see the hydraulic system is still moving. There are 6 lines here. There's right here where my cursor is, there's a target and actual position, and you can see the error is only 2 thousandths. There's a target and actual velocity up here, and there's an actual acceleration here. And then the green line is the control output, and you can see that we're making the valve really work. So, to show how this system improves, or how the second order system improves control, I'm going to stop the motion. So I'm going to do that by, okay. Now I'm going to go through the auto tuning procedure. And first I'm going to tune this up as a first order system. And that means it's using a normal PID with position and velocity feed forward. This is what a typical motor controller or a typical hydraulic motion controller would use. So what I'm going to do to begin with is zero out the gains. Okay, the gains are now zeroed out. And now I'm going to go through our auto tuning procedure. So we have a tuning wizard, auto tuning wizard. And I have read this many times before. We are going to move back and forth once in each direction. So there's 2 moves, 1 in each direction. And then this is where I set up the range of motion. So this has already been set up before. So now I'm going to make a move in the extend direction. So okay, we must get out of program mode first. Okay, so now we're going to move to start. Okay, this is an open loop move. And then we're going to move positive. Okay, move positive. And you can see this is the motion. We did the square wave here, or we call it M wave. And we got an error message because it oscillates so much and it doesn't finish in 1 second, but that's okay. We get plenty of information. So now I'm going to move it in the other direction. So I do a move to start. This moves at the far end. Now I'm going to move negative. Okay, this is the same error message because it oscillates so much. This generated a model. You can see the gain is 6.3 position units, which happens to be inches per second per volt. So this is capable of moving about 65 inches a second in the extend direction, about 54 inches a second in the negative direction. It's got a fairly small time constant, but that's not really accurate because this system cannot be accurately modeled with a gain and a time constant. And then we have a single gain, and we're moving it asymmetrically. So now I'm going to hit finish. Next thing to use is the tuning wizard, or the gain calculator. And I'm going to move this up to, about there. That's good. Hit apply gains. And now when I hit apply gains, it should move the gains over here. So now I'm going to move it back and forth. I have the keys already set up. So I was going to move to 4 inches at 10 inches a second with an acceleration rate of 100 inches per second squared, which means it'll take a tenth of a second to accelerate. It'll take the same amount of time to decelerate. So 2/10 of a second divided into 1 means it's got a frequency of acceleration of 5. And for a normal PID, you should have a natural frequency of about 20. But this system has a natural frequency of only about 6 hertz. So this is not going to work very well. So hit OK. And I'm going to move it to 4 inches. Okay, that's going to be a short move. Oh, you can see that's not very good. Oh, it's oscillating. Oh, that didn't work well at all. Let's move this gain down a little bit. Hit apply gains. There we go. Move to 4 inches. You can see that there's an awful lot of following air. A lot of oscillation. And that's because the system is essentially a mass on a spring, and a normal PID is not able to control it. So now what I'm going to do is show the advantages of using the second derivative gain and jerk feed forwards. So I'm going to go through the auto tuning procedure again. I'm going to use an existing plot. I'm going to use the same data that I had used before. So I'm going to use an existing plot. Okay, there's going to be 2 plots, one in each direction. And this is the one that we did for the extend direction. And this is the one for the negative direction. And it calculates out the same parameters that we had before. But now I'm going to go into the advanced tuning mode and remove the limit to first order tuning. So now it does second order tuning. Now it calculates out different system gains and a natural frequency of about 6.4 hertz, a damping factor of 0.1, or here 0.15. So now this should tune up much more, well, be much smoother. So now I hit finish. Now I can come over here and you can see that it's filling in the second derivative gain. It's labeled as double derivative gain here, double differential. And I'm going to move this up. I can move the bandwidth up much higher. About 1.8 is good. Hit apply. Now I can move this in the retract direction. And you can see the motion is very, very smooth. The target and actual positions are right on top of each other. Go back the other way. So the point of the whole demonstration is using the second derivative gain makes it so that you can control a system very well with a cylinder that has a natural frequency that isn't 4 times the frequency of acceleration. Remember, this is a cylinder with only a natural frequency of 6.4, not 20. So what does that mean to you? Well, first thing is that if you're a controls person and the hydraulic designer designed the system wrong, if there's any chance of tuning it correctly, it's going to be with using the second derivative gain, the advanced control system. The other thing is if you're a designer and you want to save a little money, you can reduce the natural frequency of the system down to only about 2 times the frequency of acceleration and still be safe. You still get excellent control. So what does that mean cost-wise? Well, the diameter of the cylinder is roughly proportional to the natural frequency. So if you can reduce the natural frequency by about a factor of 2, you reduce the diameter of the cylinder by a factor of 2, but that reduces the area by a factor of 4. That means that you're reducing your pump size and your valve size by a factor of 4. And that's all money. That concludes the demonstration.